This problem has us find the total solution for a damped forced system, and we're going to see how the response of the system is going to change as the driving frequency changes. So part one is having us find the solution we'll call x of t for the response of our system, and this is going to include the transient phase and the steady state phase. And in part two, we want to see just how the steady state is going to change when we change the driving frequency. In part one, we'll use a driving frequency set at 10 radians per second, and then part two, we'll let it vary. So either way, we are going to first need to make a model of our system. Now, here they give us pretty much all the information we're going to need. They already say it's a 1DOF system, and we're given the equivalent M, C, and K. So really in the modeling step, there's not going to be much for us to do. I'll just copy down. We have 10 kilograms as our mass. We are damped at 20 newton seconds per meter, and a spring constant 4,000 newtons per meter. And we have a forcing with an amplitude 100, and it's a cosine 10t. So our F naught that we're going to use is 100 newtons, the amplitude of our forcing. And we take this information and we can easily form our equation of motion for this system is going to be 10 x double dot. Let's just make a schematic of what the system is going to look like. So just a simple spring mass damper system, and we will have this forcing acting on it. So 10x double dot plus 20x dot plus 4,000 x equals 100 cosine 10t. So we can identify what we have here. Left-hand side, we have x is our only dependent variable, so 1 degree of freedom is going to be our system. And we're linear, and we are going to be damped because we have that x dot term, that 20x dot term, means we have a damped system. Now we will be concerned, is it underdamped, overdamped, critically damped, which we're going to see in a moment. We see the right-hand side is going to be non-zero. We have a dependent, an explicit dependency on t on the right-hand side in that cosine. So it's forced, but it has a constant amplitude, and it is a simple harmonic. So we have simple harmonic cosine forcing. So we have almost all the relevant information. We do need to have that additional piece to see what kind of damping we have, and we'll look in our parameters in a moment to find that. We have a driving frequency, at least in part one, is set to 10 radians per second. And we want to find our natural frequency, which will be that k over m, root k over m. And going back to our equation, that is 4,000 is our k in base units over 10. So that was newtons per meter, and kilograms for our mass means that our natural frequency is 20 radians per second. Now we can go and find our damping ratio, and we want this so that we can determine, is it underdamped, overdamped, critically damped? And that will be calculated with C over 2m omega n. And our C in base units, 20 newton seconds per meter, over 2 times our mass times the natural frequency, which we just found. So we have 1 over 20. I'll leave it as a fraction for now. And that's less than 1, so we are underdamped. So coming back to our identify, because our zeta was between 0 and 1, we know we have an underdamped system. And that's fortunate because we can only, for forced damped systems, look at underdamped right now. So we can formulate what the closed form solution generally should look like for x of t. The x of t is going to have the form of this x, big X0, e to the negative zeta omega n t, cosine of our damped frequency times time minus the phi naught term, plus x cosine omega t minus phi. So we have our steady state is going to be the second part. This is our steady state solution. And then we have the transient, and that is coming from the homogeneous part of the solution. So it's not, we have some things extra filled in. I'll just mark it as the homogeneous part, and then this is the steady state, which is also coming from the particular part. So the parameters we're going to have for the homogeneous part, that big X naught, and we have phi naught. From the steady state part, we have X, we have phi, and we're going to have the ways to calculate those. The driving frequency we've identified. We need to also identify our damped frequency before we get into the rest of these parameters. So the damped frequency is going to be, for an underdamped system, omega n, 1 minus zeta squared, the square root of that. Because our zeta is really small, this comes out to also about 20 radians per second with some rounding there. So with very low damping, we get pretty much the same damped frequency as we have our natural frequency. And one more parameter we will need, I'll copy it down here again, is our F naught. The amplitude of that forcing function is 100 newtons. We'll have these for the two amplitudes, the x naught and x, which we'll calculate in a moment, and then the phi and the phi naught as well. And those are going to partially depend on, well, the x naught and the phi naught are going to depend on our initial conditions. So I want to copy those down here so we have everything in place to figure out the rest of these coefficients. So we were told that x naught was 0.01 meters, so that's in base units, and our x naught dot, which was just written as v naught, so initial velocity 0. So we need to find the x naught, the phi naught. I won't copy them again, but referring back to when we have an underdamped simple harmonic forced system, these are the formula we want to use for x and for phi. And then we can find the x naught and the phi naught once we put in also the initial conditions. We'll calculate them again once we get into MATLAB, but just so we have the values for now. We get x is 0.03 repeating meters. The x naught calculation, get 0.0218. For phi, we'll get 0.06 radians. And for phi naught, we get a negative 3.0884 radians. So we're ready to assemble based on all the values that we just found and what we know the solution is going to look like from the identify step. So our total solution for x of t will be the homogeneous part plus the particular part. So just copying down the values that we have from above, we get 0.03 as our amplitude, cosine of our natural frequency times time, or the driving frequency times time, minus 0.06 repeating, and that's radians. So that is going to be the steady state part of this. And then the transient or homogeneous part, we're going to take the 0.0218 amplitude times e to the negative zeta omega n. That's 1 over 20 times 20 is just going to be 1, so we're left with minus t, times the cosine of our natural frequency times t, minus our phi naught term. So it's negative, so it's plus 3.0884. And again, just to identify the different parts here, this second part that has the exponential is as time gets larger and larger, this whole part is going to go to 0. This is the homogeneous part of our solution. And then this other part that's just going to keep oscillating at the driving frequency is our steady state or particular solution. Now we can take this into MATLAB and we can plot it and see what the total response is going to look like when we drive the system at that 10 radians per second. Going into the MATLAB, I'll put in all of the given parameters from our system and calculate the natural frequency, the damping ratio, and the damped frequency. And we get here the same values that we hand calculated. So 20 radians per second, 0.05 or 1/20th for our damping ratio, and 19.975, so pretty close to 20 for our damped frequency. Then we can calculate the other parameters that we need. So the x and the phi, 0.03 repeating, 0.06 repeating for the phi value. And then our x naught and phi naught, getting those same values and just plugging in the equations from the slides. So we can take those values and we can assemble our total solution. So for the time, I'm going to run this for 10 forcing cycles or forcing periods. So the period is going to be based on here the driving frequency. So 2 pi over the driving frequency is going to be the period, at least at steady state, that this is going to adhere to. So it will have a period of about 0.62 seconds, 0.63 seconds. So I'll do it for 10 of those forcing periods. Now we will see the transient part and the steady state part using this total solution. So that's what my figure 1 is going to be. And we get our plot. On the top, I have the forcing. Well, that's just repeating. That's just that 100 cosine 10t. So as a constant period here of 10 radians per second is the frequency of it. And we see amplitude 100 down to negative 100. Now we see the total response of our system. So notice that for the first 1, 2, 3, 4, 5, 6, even 7 of these periods, the oscillations are not constant. It's still going to be changing. It's still developing. So what we see here for that first 7 or so periods, we are in the transient phase. So the homogeneous part is still having an effect. We still have that second oscillation happening at the natural frequency, but it has that exponential decay going on. So as time goes on, the exponential is getting smaller and smaller, so the homogeneous part is having less and less of a contribution, and then what we have left by the time we get to the 8th, the 9th, the 10th cycle about here is we have our steady state response. Our oscillations in our system are at the same frequency as our driving frequency, the 10 radians per second. So analytically, we see what our solution looks like, and now we've plotted it. And we couldn't do this before in system dynamics. In system dynamics, we limited the scope of our analysis of forced systems to be, again, simple harmonic like we see here. However, we only looked at the steady state response. We didn't look at all at the transient response, at least using like the Bode diagram. When we simulated it numerically using ODE 4.5, then we could see the transient response, but we were never coming up with the closed form solution for the total response of the system. And here we are able to do that completely in the time domain. Now let's look at the second part of the question. Just looking at the steady state response, how does it change as the driving frequency changes? So we're not going to be locked into the 10 radians per second. What happens if we let it go from very, very low, near 0, to a very high frequency? What can we expect to change in the frequency response? So really what is going to change there is going to be, at least as the steady state response goes, is the particular solution. So how is the x and the phi, that's the only part that goes into the steady state solution. The x naught and the phi naught only are affecting the homogeneous part. But in the steady state, how is its amplitude going to change, x, and how is the phase going to change, phi, if we allow omega to vary. Going back to the slides and what x and phi are, so what we're going to do here is f naught is going to be fixed, k and m and c are going to be fixed. So what we want to do is we can keep calculating an x by changing omega. So we can try omega's 0.1, 0.2, 0.3, find the x values. Same thing for phi, this phase. And actually what we're going to do is, instead of just calculating the x, we're going to calculate the ratio of x over f naught. So we're going to see how the ratio of the output amplitude to the input amplitude is going to change as the value of omega changes. And we'll just do this right in MATLAB using, again, the same equations, but letting omega vary for our plot. In MATLAB, I can define that amplitude x function as a function of omega, which I'm calling w here in line 176. And then phi, the phase, I can also define in terms of omega. So I'll be able to calculate these for any value of omega. So what I'm going to do is I'm going to try or put in omegas from 10 to the 0 to 10 squared. So that's going to be from 1 to 100. So notice here I'm using a log space, and that's because I'm going to be representing my x values and my phi values in log space or in a log scale. So I'm going to make a figure where the top, I'm going to plot my amplitude, my output amplitude, and I'm going to divide it by that input amplitude, which was 100 newtons. And I'm going to put that ratio in decibels. So I'm taking 20 times the log 10. So the reason I'm going to be representing it this way will be apparent once I create it, because this is going to match exactly what we saw in system dynamics, because really what I'm doing is analytically making a Bode diagram. So my x scale is going to be log scale for my frequency, and my y scale, that ratio will be in decibels. And then I'm also going to make a plot of my phase, phi, and it's going to naturally come out in radians, so I will convert that to degrees. And again, the x will be in log scale and the y will just be a linear scale. So essentially all I'm doing is I'm going to find the x and the phi values for frequencies between 1 and 100 radians per second and plot it. And this is the figure that comes out. So like I just said, really all this is a Bode diagram. Now, the Bode diagram we made differently in system dynamics because we went into the Laplace frequency domain and then were able to construct it, well, let MATLAB construct it for us automatically, but we had a slightly different way of figuring out that magnitude and that phase. This is showing that exact same thing that we get from letting MATLAB make the Bode diagram, but from this analytic method in the time domain. So if we see here in the x-axis, that is the driving frequency or the input frequency from 1 to 100 radians per second. And the top plot, I'm showing the magnitude. That is, again, the ratio, really the absolute value of the ratio of my output to my input amplitudes. So that x divided by f naught. And that's being represented in decibels. And then the phase in degrees. Right, so just for comparison, before we look at this a little bit further, I will also make this using the Bode diagram, the built-in Bode diagram maker in MATLAB that we used in system dynamics. So I can define my system as a transfer function. So this is just a simple spring mass damper system. So if we recall, the standard is going to be this 1 over ms squared plus cs plus k, and that's what we're seeing here when we make the transfer function. And then using Bode to have MATLAB make the Bode diagram. So this will be another figure. So we can compare what we got doing it with a manual method to what we get using Bode in MATLAB. I'll put them side to side here for comparison. All right, so if we look at the magnitudes, we are seeing, just for one-to-one comparison here, a pretty much flat, a little bit less than -70 decibels, and then it starts to rise up. And we'll look at what point that peak is at on both of the diagrams. Should be essentially the same, depending on how close I got. So we see 20 radians per second is the peak, and again, around 20. I'm not quite at the peak now, I am. So the same omega value of 20 on both of these diagrams here. And the real difference we see is in the phase. We see in the one that we did manually, it goes from 0 degrees, and then it has that inflection point at also that 20 radians per second. And then it's going to go up to asymptotically approaching positive 180 degrees. Whereas in the using Bode, we're seeing kind of the opposite happen. It starts at 0 degrees. We have that inflection point still at around 20 radians per second, and then it asymptotically is approaching negative 180 degrees. So this difference is coming due to how we are defining the phase, the way we're doing it in this course, where we're saying that the phase is going to be inside that cosine term, that omega t minus phi. And if we remember from system dynamics, the phase was actually defined as a positive. It was omega t plus phi. So our definition of phase has the opposite sign in this course as it had in system dynamics, but physically, we're talking about the exact same thing. So here on the left, we are going to be, let's say at high frequencies, subtracting a positive 180 degrees, whereas here on the right, we are adding a negative 180 degrees. But that's exactly the same thing mathematically that's happening. It's just differing in how we defined the two. So we were able to make our own Bode diagram just from the definition of the amplitude and phase of that steady state part of the solution, or the particular solution to our problem. So let's see what happens here. At low magnitudes, we're at this pretty stable ratio between the output and the input amplitude, so around -72 decibels. And then we have this peak, and we're seeing that that is at about 20 radians per second, and that is coinciding with the natural frequency, also the damped frequency of our system. So we have a spike in magnitude, like we expect for a 1 degree of freedom system, like we saw in system dynamics, that the output amplitude is relatively going to get very large at or near that natural frequency or damped frequency. Now, it depends how much damping we have, or what the damping ratio is, exactly where that peak is going to be. But for low damping, like we see here, where it's only 1/20, we see that it's very, very close to that natural frequency of 20. And then at higher frequencies, that magnitude is going down. And that's going to be typical for a damped 1 degree of freedom force system. Is if the driving frequency is at or near the natural frequency, we're going to have a peak. For large driving frequencies, the magnitude is going to start to go down. And for low driving frequencies, we're going to have a fairly consistent magnitude, the ratio of the output to the input. And for the phase, we're starting at being in phase, so a phase of 0 degrees. So our output is going to, peaks are going to match the input peaks, and the valleys the same way. It's going to start to, in this case, increase, have an inflection point at the natural frequency, and then at high frequencies, we're going to see that we're going to go into antiphase. The peaks of the input are going to be at the valleys of the output, and vice versa.